Hello and welcome to our presentation on the Connectome and what it means for neuroscience. Myself and Bailey will be presenting on behalf of our colleagues Jane, Fatima, Parisa and Shams. Today we'll be giving you an insight to what the Connectome is, a brief history, how the Connectome is created, the benefits and implications surrounding the field of neuroscience and what it means for the future.
The Connectome is a complete map of all the neural connections in the brain. These neural connections are believed to play a role in the control of human behaviours, abilities, memory, and even some diseases such as Alzheimer's disease. The ultimate goal is to have a comprehensive map of all the neurons and synapses within the brain, and it is hoped that this will provide revolutionary breakthroughs similar to those of the Human Genome Project had for the field of genetics.
Currently, the only organism that has a complete connectome is the roundworm C. elegans. This organism is 1.5 millimeters and has around 300 neurons and 7,000 synaptic connections. Completing this connectome took more than 12 years of work, as each individual neuron was identified manually under a microscope and its projections to other neurons were traced by hand. The diagram shows the connectome of the C. elegans neural system. Each node represents a neuron, while the lines represent the connections between these neurons. The larger nodes represent major junctions and control systems within the neural system. This organism seems to have a very complex connectome with thousands of connections. However, the human brain has 100 billion neurons and 700 trillion neural connections. This gives an idea of the complexity and time-consuming practice of mapping just a small part of the human brain, yet alone a complete connectome.
Presently, the only recognised technique of mapping a connectome is tracing each individual neuron with the human eyes using microscopic images. This method involves the use of three-dimensional microscopic images where each individual neuron or synapse is identified by differing colours. This technique is very time-consuming, lacks validity, and can be seen as an unreliable visual of the human connectome. Therefore, scientists are working on developing and incorporating new technologies that will help with the construction of the connectome. Current researchers are using diffusion and functional MRI for the reconstruction of the neural pathways. Electroencephalography and magnetoencephalography coherence are also used for functional connectivity analysis as they measure the electrical and magnetic fluctuations in the brain.
There are many theories currently being hypothesized about the connectome. MIT professor Sebastian Sung, one of the leading researchers in the field, envisions the brain neural connections as a stream bed through which our consciousness flows. The graph theory analysis uses mathematics and sociology to understand how human cognitive functions are linked to neuronal network structure. Previous studies have been conducted using an EEG to map out the brain's network organization during aging. The study was able to map out the boundaries separating physiological from pathological neurodegenerative brain aging by using graph analysis. Graph analysis uses a set of nodes or brain regions and links anatomical function and effective connection to identify functional connectivity networks. The graph theory may be the key to providing pathophysiological processes underlying brain disconnections. Leo and others believe that connection strength between the neurons has a limitation on the amount of information that is able to flow per unit of time. The advantage of this theory is that it uses real information regarding the flow in the brain network and combines it with the weighted connectivity data. This theory contradicts with the graph theory, and further research into the structural and functional connectomes at neuronal level is needed. There are currently hundreds of theories about the connectome, however no scientist is able to prove that their theory is correct. More technological advances are required in order to come to a conclusion about the human connectome.
The connectome has the potential to revolutionise our understanding of the brain, its functionality, as well as providing us with more insight into human behaviour. For instance, a study published in the Journal of Social Cognitive and Affective Neuroscience explored how the connectome, specifically data pertaining to the cortical thickness, may be used to determine a subject's personality. Additionally, the connectome may help scientists to better comprehend the complex mechanism behind memory storage. By examining how memories are retained, we will be better equipped to diagnose and treat memory disorders, such as dementia. Furthermore, it is widely accepted that mental illness is caused by the degradation or abnormalities in neuronal connections. The connectome can be used to develop more effective treatments for these conditions. Finally, scientists have utilised the connectome to examine a possible link between an individual's intelligence and the extent of neuronal connectivity in their brain, emphasising that neuronal mapping can provide us with a more objective method of calculating intelligence.
Despite the advantages of the connectome, many argue whether or not it will be completely mapped out. Sung estimates that it would take 100,000 years for a lone worker to trace the connections in 1 cubic millimetre of brain tissue. Additional dimensions, such as fine structure details like the number of vesicles at synapses, or even the molecular subtypes of the neurons involved, make it difficult to determine the completion of the connectome. For some scientists, a simple diagram of connections between neurons might be able to complete map, while for others it might be important to add the spine shape of the neurons. Hence, these additional dimensions add to the complexity of the completion of the connectome, and also lends to the debate of whether these minute structural details are necessary in the mapping of the brain, and whether they contribute to our understanding of neuroscience. Despite these challenges, based on current research, the mapping of the brain has led to many significant discoveries. Further advancements in technology will continue to aid in the complex mapping process of the human connectome. Sebastian Seung signifies the importance of the connectome and what it means for neuroscience through his TED Talk and famous words, "I am my connectome."